Hello. Here we are looking at a partial fraction decomposition question where we have the denominator already factored. It's a cubic, and the degree of the denominator is more than the degree of the numerator. So you can start the process. Double check to make sure the interval -1 to 0 does not contain any places where the denominator is 0 at, and x equals 1/3 is the only place where the denominator is 0. So that's not in our interval. So we're good to go. And we have to start by recognizing what type of term the denominator is. So 3x minus 1 is a linear term, and x squared plus 1 is an irreducible quadratic. Based on the type of term, that'll tell you the decomposition. A linear term gets a constant on top of it, but an irreducible quadratic term gets a linear term on top of it. So if we start with a over 3x minus 1, then the linear term will be called bx plus c, and that'll be on top of x squared plus 1. Now, our job is to find the a, b, and c that make this happen. So how are we going to do that? Well, it comes from trying to put the fraction back together. Combine the fractions multiplied by the part of the denominator that you're missing. So the a fraction gets multiplied by x squared plus 1, and the bx plus c fraction gets multiplied by 3x minus 1, both numerator and denominator, to give us the original fraction. And everything now will focus on the numerator. Now that we have the denominators matching, we can combine the numerators, and we have the equation that governs the solving of a, b, and c. Now, what you normally do is, for a shortcut, you can let x equal the numbers that make the linear term 0. If you were to let x equal 1/3, it brings in the fact that the bx plus c term will be zeroed out, but the 1/3 going into the rest causes some pretty bad arithmetic for the letter a, to find the letter a. So I've done that for you. I've made it simpler by saying the hint that -7 is the constant in the numerator of the fraction with 3x minus 1 in the denominator. So I'm letting you know that a is -7, saving you the drama of having to do that fraction arithmetic. So then we'll go find b and c, and we'll do that on the next slide. So what happens then after you let all of the linear term, let x equal all of the numbers that would make the linear term 0, then you want to start picking something that's convenient to plug in. You know, like x equals 0 if it hasn't already been chosen. It's great to plug in. It kills a lot of the terms and makes it easier to solve. What's nice about x equals 0 is it'll kill the need for b, because b is multiplied by x. And so what we'll end up with is a -7 times a 1. But the b is gone, and then it'll be c times a -1. And then the right-hand side will just be the constant term, -10. So add that 7 over, we'll get a -3, and then we'll divide by -1 or multiply by -1, and we know the value of c now is 3. So we know a, we know c, we can go get b by picking something else convenient to plug in after 0. If you haven't already used it, then with 1 is great. We'll end up with a -7 times a 2, a b plus a c, but we know c, go ahead and plug it in as 3. And then that'll be multiplied by a 2, 3 minus 1. And on the other side, 5 plus 5 minus 10 zeroes out. So you'll add that 14 over and divide by that 2, and you'll end up with the fact that then b plus 3 must be 7 or b must be 4. All right. You're out of the algebra minefield. You found the values of a, b, and c. Now you're back in calculus where you want to be able to integrate. The whole purpose was to break this into simpler fractions, simpler meaning simple to integrate. And the 4x plus 3, the bx plus c part, when you have an irreducible quadratic who is of the form x squared plus a squared, when it's time to integrate, you want to break that apart into 2 separate fractions, with the 4x on top of the x squared plus 1 and the 3 on top of the x squared plus 1. Okay. Reason being is that we can get those integrals separately, but together we couldn't do it. And so, go to the next slide. Let's work this integration. Now, it's going to be a natural log for the first one, but there's going to be a factor of 1/3 you have to incorporate. It's going to be a natural log for the second one, but there's going to be a factor of 2 you have to incorporate. And the third one is directly the derivative of arctan. So the antiderivative would be just arctan. How, if you need to, work a U sub and you'll see it works out. I have it all written up here. Pause the video and work through it. Here's the U sub for the second one. And now we're ready to plug in the bounds. You plug a 0 in every place you see an X. You plug a -1 in every place we see an X. Okay? Be sure to use absolute value bars because we're looking at a -4 inside of a log. So what's nice about this is that when you plug the 0 in, you get the natural log of 1 twice in both cases, in the arctan of 0, and all those guys zero out nicely. On the other hand, over here with the -1 being plugged in, that's going to be the log of 4 and the log of 2 and the arctan of -1. Okay, all these guys zero out on the upper limit, and then go ahead and distribute that negative across for the lower limit. And upon doing that, what will happen is we can combine the logs together. 2 log 2 is really log 4. You can bring the exponent up. And so if you have -7/3 of log 4 and you add log 4, that's like 3/3 of it, you have -4/3. And so finally then we finish up with 7/3 log 4 minus the log 4 to give us the 4/3 of log 4. And then the pi over 4 is the arctan of -1. And so that is it.